So now that we've talked about entropy with respect to spontaneity of a process, we're going to look at a new construct called Gibbs free energy, or sometimes just referred to as free energy. So Gibbs free energy is represented by the capital letter G, as you see here. Okay, and basically this free energy is related to both the enthalpic and entropic values associated with a specific reaction. So if we go ahead and look at our free energy and its relationship to spontaneity, we can utilize our previously discussed understanding of entropy and its relationship to spontaneity. Okay, so if we take the equation that we have here, okay, this gives free energy equation, and we divide both sides by negative delta T, we end up with the equation that you see here. Now recall the delta S of your surroundings, or the entropy of your surroundings, is equal to the negative change in enthalpy divided by temperature. Okay, and we discussed this in the last lecture. Okay, so knowing this, if we go ahead and plug in our delta S of surroundings for the enthalpy and temperature variable that we see in this equation right here, we subsequently end up with this equation. Now notice I've indicated surroundings as well as changed this delta S to the system because we do know that our delta S of our surroundings and the delta S of our system all equal the delta S of our universe. Okay, so we know that the change in the surroundings and the change in the system is equal to the change in our universe. And we know that the more positive the value of the entropy that's occurring in the universe, the more spontaneous that process is going, the more likely that reaction is going to be spontaneous. Well, we've also taken this relationship that we've discussed in previous lectures and related it to Gibbs free energy. So the change in enthalpy of the universe is directly related to the negative change in Gibbs free energy with relationship to temperature. So in a situation where you have a process that's at constant temperature and pressure, you're going to have spontaneity in the direction in which the free energy gets more negative or decreases. So basically, as your delta G value becomes more negative, the entropy of your universe increases and becomes more positive. So subsequently, a spontaneous reaction is going to have a negative delta G value and a very positive delta S of the universe. Okay, so now that we understand the relationship between our entropy and our Gibbs free energy, we can go ahead and look at some details associated with Gibbs free energy. Okay, so what are some considerations or some things to think about? Well, both entropy and free energy, so your delta S of your universe and your delta G values are able to predict spontaneity. You know, the more positive your entropy value, the more spontaneous, the more likely your reaction will be spontaneous. In that same way, the more negative your free energy value, the more spontaneous, more likely your reaction will be spontaneous. So what you need to know is that the entropy of the universe, that delta S, okay, that delta S of the universe, okay, applies to all processes, and can subsequently sometimes be difficult to nail down because of the variables being considered. Okay, free energy, on the other hand, can only be used on processes that are occurring at constant temperature and pressure. And so since that's the case, most reactions or most processes that we observe or pay attention to occur in this situation at a constant temperature and a constant pressure. So the free energy is easier for us to basically calculate or come up with, and subsequently ends up being the more useful of the two with respect to predicting spontaneity. So let's go ahead and let's look at the Gibbs free energy associated with the melting of water in its solid state to its liquid state. Okay, we've been given our enthalpy and entropy values respectively for this process, and what we're going to do is we're going to look at this process at 3 different temperatures. So negative 10 degrees C, 0 degrees C, and positive 10 degrees C. Okay, so what we want to consider is, first of all, how are we going to compare each of these temperatures? Well, we need something that will allow us to make a direct comparison between these three temperatures utilizing enthalpy and entropy values. Okay, and so we just learned about Gibbs free energy, so we know that our Gibbs free energy is going to be equal to our delta H minus T delta S. Okay, so we know that we're going to use Gibbs free energy in order to figure out or compare the spontaneity of this process at these three temperatures. Okay, so what do we need to do? Well, first of all, what we need to do is we need to consider what we've been given. Obviously, we've been given these three temperatures. Okay, we've also been given our enthalpy value, which is the same for each of them, our entropy value. Okay, so we can utilize these two values to plug into our Gibbs free energy equation. Okay, so before we plug anything in, we need to make sure that everything is in the appropriate units. Okay, so notice we have joules per mole and joules per Kelvin mole. So our joules match up, so this will be a straight up addition or subtraction. We don't have to worry about any of the units needing to be adjusted here. Okay, the other thing that we're going to do is we're going to convert our degrees Celsius into Kelvin. Okay, and so these are the temperatures in Kelvin for each of the temperature values that we are discussing. Okay, so what we're going to do is basically plug in our delta H, okay, and subtract out the temperature times my delta S value, okay, and that's going to give you, for this first example, plus 2.2 times 10 to the second. Okay, we're going to do that same process for our temperature 0 as well as our temperature of 10 degrees C. Okay, and we get these various delta G values. So remember, when you have a negative delta G, that means your reaction is spontaneous. So we have a negative delta G here, and our negative delta G indicates that at 10 degrees C, we have a spontaneous reaction. Now, if we look at our negative 10 degrees C calculation, we notice that we have a positive value. Okay, so a positive value is going to correspond to a non-spontaneous process. So going from solid to liquid for water at negative 10 degrees C is a non-spontaneous process. Okay, so that should make some logical sense, I think. Now, the process of going from solid to liquid is non-spontaneous, but we know that the opposite process, the going from a liquid to solid, will be spontaneous. So remember, if a forward reaction is not spontaneous based on our Gibbs free energy, the reverse process will be spontaneous. Okay, now at 0 degrees C, okay, I want you to notice that our Gibbs free energy value, our delta G value, is 0. Okay, and so what that means is that you are at equilibrium. Okay, the tendency to go towards the liquid or go towards the solid is basically equal, and the two states coexist in tandem. So there's a dynamic equilibrium, and you subsequently have both present. Now, something else I want you to notice here in this table is that we could have also looked at this with respect to the delta S of our universe. Okay, so remember, the Gibbs free energy, the more negative, the more spontaneous. With respect to the delta S of your universe, the more positive it is, the more spontaneous. So if we look at the delta S of the universe values that we calculated, okay, obviously using our delta S of surrounding calculation, utilizing our enthalpy and temperature, as well as plugging in, the delta S not associated with our change here, we end up seeing the same type of product or the same type of conclusions. We have a positive entropy value for the delta S of our universe at 10 degrees C, so that means it's a spontaneous process. Notice at negative 10 degrees C, the value for our entropy change is negative, so that implies that it's a non-spontaneous process. And of course, just like with Gibbs free energy, our entropy value is 0, indicating that we're at an equilibrium situation. Okay, so basically, guys, our Gibbs free energy equation, if I have a negative delta H and if I have a positive delta S, that means that both my delta H and delta S components of this equation will both be negative, or at least be contributing negative values to the delta G. The more negative you are, okay, the more spontaneous you're going to be. So in this case, they would both contribute negatively to the delta G value, so you'd have a spontaneous reaction. In the case of a positive delta H as well as a positive delta S, the spontaneity of your reaction would depend on your T, okay, your temperature. Okay, so the larger your T value, the larger this component of the equation is going to be, and subsequently this negative value will hopefully cancel out the delta H that is positive, and subsequently still give you a negative delta G. So at high temperatures, this situation will give you a spontaneous reaction. Okay, if I have a negative delta H, okay, as well as a negative delta S, right? If I have a negative delta S here, the negative and the negative is going to give me a positive value. So T, once again, is going to dictate the contribution to delta G. The smaller T is, the less positive this contribution will be, and subsequently give you a spontaneous reaction. Now, if I have a negative delta S and a positive delta H, okay, these are both going to contribute positively to the delta G value, so you won't have a spontaneous process for the reaction you're looking at. However, the reverse process will be spontaneous. Okay, so standard free energy change is basically dictated or related to the state of your reactants and products. Okay, so the change in free energy that occurs if the reactants in their standard states are converted to the products in their standard states is the situation that we're looking at here. And we indicate this by this not symbol. And we've seen this before. Okay, and we can use these delta G naught values to compare the relative tendency of a reaction to occur. So still with the same thought process, the more negative the delta G naught, the more spontaneous your reaction is going to be. So in that same thought process, the delta H and delta S values are going to impact the reaction in the same way that we discussed in the previous slide. Okay, so in the practice problem here, they're asking us to calculate our delta H naught, our delta S naught, and our delta G naught, okay, for a specific reaction at a specific temperature, which is 25 degrees C. Okay, so the reaction that we're dealing with is the following. Okay, we have basically these two gases coming together to form a new gaseous product. Now, they want us to calculate each of these individual pieces. Now, delta H and delta S can easily be calculated from the tabulated data that we've been provided. Okay, now delta G, on the other hand, is going to be calculated utilizing the delta H and the delta S values that we calculate. All right, so we've learned how to calculate our delta H and our delta S values from tabulated data in the past. So we're going to go ahead and do that, and then we're going to look at the calculation of our delta G naught. Okay, so delta H is going to equal the summation of our products minus our reactants. Okay, and the same is going to be true for our enthalpy value. So delta S is going to be equal to the above. So let's go ahead and plug those numbers in. Our delta H is going to be equal to our products. So there's 2 moles of our products. Okay, which is SO3, so negative 396 kilojoules per mole. Okay, so that's our product, right? And then minus our reactants. Okay, and we have let's see, we have 2 moles of the SO2, which is our reactant, negative 297. Okay, and then obviously oxygen has a value of 0 here, so it'd be plus 0. Okay, go ahead and plug that in your calculator. Right, those molar amounts cancel the mole units that we see here. So moles and the moles out here are going to cancel. Kilojoules is what are left over, and we end up with this value for our change in enthalpy. Okay, we're going to do the same type of calculation for our entropy change. Okay, so once again, it's going to be products minus reactants. So 2 times 257. Okay, in this case, we're dealing with joules per Kelvin mole. Okay, so once again, we have 2 moles out here for our products. Okay, and then we need to consider our reactants. So we have 2 moles of SO2. SO2 has a 248 joules per Kelvin mole. Okay, and then oxygen has a value of 205. Okay, and there's only 1 of them. Okay, so we go ahead and plug that in your calculator. You'll get this value for your delta S variable. Okay, so now we need to utilize these 2 values in order to calculate our delta G. Now remember, delta G is calculated by using our delta H minus T delta S. Okay, now there's a few things that we need to consider before we just plug the numbers in. First, we need to consider units. Okay, so notice we have kilojoules here and joules there. Okay, kilojoules and joules obviously cannot be summed directly, so we need to make sure that we convert one or the other. Okay, so in this case, we're going to convert our entropy value to joules, to kilojoules, so that this calculation will be straightforward. Also, notice we have the units of Kelvin here, so our temperature is given in 25 degrees C, so of course we need to convert that to Kelvin when we plug it into our equation here. Okay, so our delta G value, our delta G naught value is going to be equal to negative 198 kilojoules. Okay, and that's going to be minus 298 Kelvin times negative 0.187 kilojoules per Kelvin. Okay, and if you go ahead and plug that into your calculator, okay, that's going to give you negative 142 kilojoules as your Gibbs free energy. So the process that we're looking at here is a spontaneous process. We know that because we have a negative value for our delta G. And as you can see, the calculations for each of these individual pieces, the enthalpy and entropy steps are used to calculate our Gibbs free energy, which tells us the spontaneity of that reaction in a very clear, direct way. Okay, we could also use the method of adding reactions to calculate our delta G. If we know our overall reaction that we're looking for, and if we have reaction steps that will in fact sum to the overall equation and their corresponding delta G values, we can basically use the Hess's law approach to calculate these values. Okay, so remember that we want to get the overall equation from these individual steps. Okay, so in order to do that, the first thing we're going to need to do to this first reaction here is we need to flip it, okay, because we want to have our carbon monoxide on this left-hand side. Okay, for our reaction number 2, okay, we're going to need to multiply through by 2 in order to get our corresponding pieces to cancel out in the appropriate way. So if we go ahead and look at this, what cancels? 4H2O, 4H2O. Okay, I have 4 O2 and 3 O2, so I have 1 O2 remaining here. Okay, my CH4s, okay, they're going to cancel out. Okay, and what I'm left with is 2 COs, 1 oxygen and 2 CO2s. Okay, so much in the same way that we've utilized this reaction addition method to calculate our enthalpy values, we're going to do the same thing here with our change in Gibbs free energy values. So we reversed this reaction. Okay, so we're obviously going to change the sign of the delta G value. Okay, so it's going to become positive. And for this delta G, we multiplied the reaction through by 2, so we need to multiply that delta G value by 2. Okay, and then if we sum these two, we end up with this as our final delta G value for the process. And this is a spontaneous process because our delta G value is in fact negative. And of course, we can also use the standard free energies of formation values, so basically the tables from the back of the book, to calculate the delta G of the reaction. Okay, so similar to what we did in one of the earlier examples today, when we calculated our delta H and our delta S naught, we can do that same approach with the components for our delta G naught of formation values. Okay, and basically the delta G naught of formation values are the change in the free energy that accompanies the formation of 1 mole of that specific substance from all of its other elements in their standard states. So we've already kind of looked at some of these components before, but this is just with respect to Gibbs free energy and the calculations we get. Okay, so if we're going to look at the production of glucose, notice these are the constituent elements, okay, in their standard states. We're producing 1 mole of that product. And so basically, how would we go about calculating this? Well, we go ahead and we look up the Gibbs free energy values. Okay, so we get this from a chart. Okay, there's only 1 mole of it, so it would be 1 times that value. Okay, there's 6 moles of the carbon. Okay, we look up that value, sum it with 6 moles of the hydrogen formation value, and 3 moles of the oxygen formation value. Okay, and if we go ahead and add up all these pieces, okay, we would subsequently get our delta G naught for this process. Okay, and so something to remember, similar to what we've seen in the past, the delta G naught formation values for an element in a standard state are going to be equal to 0. Okay, so this should harken back to enthalpy values that we looked at several units ago. Okay, so let's go ahead and let's actually look at the calculation process for an example. Okay, so remember we said that our delta G naught of your reaction is going to be equal to the summation of your products delta G naught value minus the reactants delta G naught values. Okay, and we'll go ahead and show that calculation out. Okay, so we've been given the tabulated data for our delta G naught values. Okay, so delta G naught of your reaction is going to be equal to, okay, so products, we have 2 moles of CO2. Okay, so 394 kilojoules per mole plus 4 moles of H2O in its gaseous state. Okay, so minus 229. Okay, and when you guys are looking at the charts and the tables, make sure that you're paying attention to the state that the component is in. Okay, you don't want to plug in the incorrect values because you're plugging in liquid values instead of gaseous values. Okay, so now that we've calculated or plugged in our product values, let's go ahead and plug in our reactant values. Okay, so we have 2 moles of methanol. Okay, so negative 163 kilojoules per mole. Okay, plus, okay, in this case, we have 3 moles times 0 kilojoules per mole. Okay, notice oxygen is in its standard state, so the delta G value, the delta G naught, the formation value is 0. Okay, so we plug this all into our calculator. We subsequently get negative 4,378 kilojoules. So spontaneous process. Okay, and we calculated this from our Gibbs free energy of formation values. So just as a kind of refresher, guys, make sure that you're paying attention to the units that you've been given. Okay, remember when you're plugging in your delta G naught values into these types of calculations, you're multiplying by the molar amounts associated with the coefficients of each of the reactants and products. Okay, so your moles and moles are canceling. And basically just make sure you're paying attention also to the states of the elements when you're pulling them from the tables. You want to make sure you're plugging in the appropriate product and reactant with the proper state of the reactants and products.